Hello and welcome to HelpYourMath.com. In this video, we're going to look at savings plans and investments. Previously, we've looked at examples using simple interest, compound interest, and maybe even continuous interest to look at different types of interest earned on accounts. But with those, we only looked at just a single deposit and what would happen over time if you just left that one deposit in the account. Today, we're going to look at when we make monthly deposits. Maybe you want to start a savings account, but you don't have $15,000 right now. So instead, you make just a small deposit each month. We're going to look at how that grows given different annual percent yields and interest rates. So let's get started with an example. We're going to try to figure out how to derive the savings plan formula, and then in the next video, we're actually going to go through the derivation of that formula. For now, we're going to suppose that we deposit $100 into a savings account at the end of each month. Let's suppose that your plan pays interest monthly at an annual rate of 12%. So if it's an annual rate of 12%, what this means is that we are receiving how much interest each month? Well, that would be 12% divided by 12. So this indicates 1% interest per month. Okay. But we also are making the assumption here is that we are beginning with $0 in this account, but by the end of the first month, that's when we make that first $100 deposit. So we make $100 at the end of the first month, another $100 deposit at the end of the second month, and so on and so forth. So I have the table set up here. Let's talk about what each column represents. We have end of month one, the prior balance, there was nothing there, so it was $0. If there's no money, there's no interest earned, and then there's $100 deposited at the end of the month. So the total balance by the end of month one is $100. For month two, the prior balance was $100. So we have $100 plus, remember there was interest earned on that. The interest earned, which we can see here, is 1% of 100. 1% of 100 is 1. So here we have the prior balance. Here we have the interest earned. And then we want to add to this the deposit that we make at the end of this month, $100. So at the end of month two, we have $201 in the account, which we can see here. Okay, we can do this same process to figure out by the end of month three, the initial balance, the prior balance was $201. 1% of that $201 is $2.01. We make another $100 deposit. And by the end of month three, there is $303.01. Let's also calculate this by the end of the fourth month. How much will we have? So we take that prior balance, $303.01, plus the interest earned on this. Remember, it's going to be 1% of this. So it's 1% of $303.01. Well, 1%, remember that's 0.01. So we move the decimal 2 places to the left and we end up with 3.03. We're going to cut off the 01 because, right, this is a dollar amount. We should end at the pennies place. And what do we do at the end of the month? We add $100. So if we add $303.01 plus $3.03 plus 100, we end up with a grand total of $406.04. So you can see the amount is growing. It doesn't seem like a lot, but every little bit helps, right? Okay, by the end of the fifth month, so for the fifth month, the prior balance, I'm going to say fifth, was $406.04, plus the interest on that would be 1% of that, or 0.01 times 406.04, plus we're going to deposit another $100. So this calculation multiplied by 100 moves the decimal point over, will be 4.06. And if we add these values together, we end up with $510.10. And lastly, the sixth month, the previous balance, the prior balance is $510.10 plus 1% interest on that, 510.10 plus our new deposit of 100. So this is 1%. That's 0.01. That's moving the decimal 2 places to the left. We end up with 5.10. So $510.10. plus $5.10 plus 100 would give us a grand total at the end of the sixth month of $615.20. Now, this was a lot of work to get to that sixth month, wasn't it? Maybe there's a formula or something that we could use. And there absolutely is a formula. Before we get to the formula, which is on the next slide, I strongly suggest if you don't have a calculator handy, go get a calculator because we're going to definitely need it with the formula. We could kind of do this work in our head, but going forward, we're definitely going to want a calculator. Okay, let's talk about this formula. Here it is. So we have the amount, that's the accumulated savings plan balance, is equal to that regular monthly payment, PMT, times, and then we have this whole mess of a formula, but you will notice that certain parts of it repeat. It looks a lot scarier than it really is. The important thing is taking your time when you plug in. So we have 1 plus the APR divided by the number of payment periods per year. All of that 1 plus the APR over n is raised to the n times y. That's the number of payments per period. The number of payment periods per year times the number of years. Then we subtract 1. What that's doing is that's just getting rid of the amount in the account, and this is just kind of converting it to a rate percent. And then we're dividing it by the APR over n. So you'll notice that this is the same. So that's nice that we have that. It's just going to be that same value that we're dividing by. And then we'll take that and we'll multiply at the end. So we see with this PMT times, but really this is the last thing we do. So the last thing we're going to worry about is multiplying by whatever that PMT is. So let's go back to that previous example and make sure that using the formula, we end up with that same amount. So what did we have last time? We are looking for 615.20. I hope this works, otherwise this formula is no good. So let's label our variables. The PMT, this is the regular monthly payment. Remember what the regular monthly payment is? $100, right? There's the monthly payments. The APR is 12%. I like to convert 12% to its equivalent decimal, so I might say 0.12, but you can also say 12%. Next, we need to figure out what n is. So this is the number of times you're putting money in the account. That would per year. That would be 12. Y is the number of years. Now we're looking at 6 months. So we don't want to say y equals 6 because that would be 6 years. 6 months we want to convert to years, and that would be half a year. So you can either say 1/2 or you can use 0.5. It doesn't matter because 1/2 and 0.5 are the same thing. Okay, we have all the variables accounted for, so let's verify this formula. And again, have your calculators handy. We have A equals 100 times, and again, this is the last thing we do even though it's shown first. We have 1 plus that APR, which is 0.12. We want to use the decimal, not the percentage, divided by n, which is 12, raised to the n times y, minus 1, all divided by the APR, 0.12, divided by 12. Now, we want to make sure that we're following order of operations, and you might have a fancy calculator that will do this for you if you plug it in like this. Most of us don't, especially the exponent. Notice that in the formula, they put the exponent in parentheses. It is so important that you do that calculation very first. So the first thing I want to do is calculate 12 times 0.5, and this just means half of 12. So the exponent here is really equivalent to 6. Make sure you do that first. Otherwise, you might raise something to the 12th and then end up multiplying by 0.5, depending on the type of calculator you have. So just do the exponent first, and then we don't have to worry about it. Next order of operations tells us do what's inside the parentheses. So we want to calculate that next. We have A is equal to 100 times 0.12 divided by 12. You can use your calculator, or you might know that 12 hundredths divided by 12 is going to be 0.01. And then we have this, remember this is going to be raised to the 6th, we're going to subtract 1, and then this should be the same value as whatever we had here, so this should also be 0.01. Okay, so now we want to raise 1.01 to the 6th power. When we do that, we end up with, let's see, 1.01 to the 6th power will end up being something like 1.06152, blah, 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 minus 1, all divided by 0.01. We subtract the 1, all right, we're getting more reasonable here, and we end up with 0.06152, blah, 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 divided by 0.01. This will become 6.15, 100 times, when we divide, this will be 6.15, 2, blah, 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 and whoo, here we are. We end up with 615.20. How'd our formula do? Well, what were we expecting? Let's go back. 615.20. And we have 615.20, so the formula worked. Hooray! So you see, we don't have to go through it step by step. And again, with the formula, I went through it step by step, but you can skip steps, or you can do multiple steps at the same time. Let's look at one more example. Thank you for bearing with me. Here we are. At age 30, Michelle starts an IRA to save for retirement by depositing $100 at the end of each month. If she can count on an APR of 6%, how much will she have when she retires 35 years later at the age of 65? Then we want to, after we figure that out, we want to compare the IRA's value to the total deposits that she made over this period of time. Okay, so first let's start by answering the question. How much money is going to be in this IRA? Let's label our variables. The PMT, the monthly payments, are $100. The APR in this account is 6%, so I like to convert to the decimal, 0.06. In this case, N will equal 12 because she's making monthly deposits. And this time in years, it says 35 years. So time is 35 years. Now we're ready to plug in. Okay, here we go. So the amount after 35 years will be 100 times, we have 1 plus the APR 0.06 divided by 12. This thing we're going to raise to the power of n times y. I'm going to go ahead and just do n times y here. I'm not even going to put it in the formula because I promise mistakes happen when we do that. So n times y will be 12 times 35, and 12 times 35 is 420. So I'm going to go ahead and plug that directly in, 420. We're going to subtract 1 from this monstrosity, and then we're going to divide this thing by the APR, 0.06, over 12. Okay, so kind of cleaning up the numerator all in one fell swoop. Following order of operations, first we want to do 0.06 divided by 12, which will end up being 0.005. Then we add 1 to that, so that's 1.005. Raise it to the 420th. That ends up being 8.12355. Subtract 1 from it. I'm just trying to save space here because I know we have a little bit more work to do. So we end up with 100 times. The numerator becomes 7.12355 divided by 0.005. And all of this, when we multiply by 100 and everything, we end up with $142,471.03. So after 35 years of just making these $100 deposits, this is how much will be in Michelle's account. So this is the IRA value in 35 years. Now the next question said, compare this to the amount that she actually deposited in the account. So if she put $140,000 into the account herself, that's not a great return on her investment. So now let's compare how much did Michelle actually deposit. So we're going to say total deposits. So remember what she did. She deposited $100 at a time, 12 times, so 12 months per 1 year. And she did this for 35 years. So she did $100 per 1 month. I'm going to do a little dimensional analysis here. The months cancel, the years cancel. We're left with the amount of money. 100 times 12 times 35 is $42,000. So she deposited $42,000. Her IRA contains $142,000. This means that her account contains more than 3 times what she deposited. So that's a pretty good deal for Michelle. I'd take it. Not a bad idea to just save a little bit at a time because it really does have a good payoff. These have been examples of using the savings plan formula. Thank you for stopping by.